All right, so the problem with Christmas tree lights is if you lose one light bulb, you lose the whole circuit. So that is not how your house is wired. Imagine if this were your, living room, and this is a lamp, and this is a TV, and this is a computer. So you're sitting with your laptop on your lap and watching TV at the same time with the light on. The light burns out, and what happens to the TV and the computer? That's right. They go to battery backup, exactly. You'll lose them because the whole circuit will be disconnected.
But that doesn't really happen.
That does not happen in your house because your house is wired in parallel. Now we're going to do parallel circuits, and they look very different. Instead of a single path, there are parallel pathways, just like railroad tracks, and the appliances are connected across those parallel pathways. So now, let's lose a light. Well, what will the other three components be able to do? Keep going, stay on, right? So you only lose that one parallel pathway. Now, there's a problem with parallel pathways, because that's like, well, yeah, that's smart. Why wouldn't we do that all the time? There is a drawback to it, and we'll talk about it in a minute, or maybe tomorrow. Look what happens to the current. Let's start with the current in a parallel pathway. So I. And I'm not going to put numbers in for the resistors. I'm just going to use the current. So let's say we have 8 amps of current coming in right here. And then, oh, what's that little spot? What do we call that? That's right. The junction. Okay, so if we split it evenly, what would each of those paths get? 4 and 4, right? Oh, what's this? Oh, looky. Another junction. Let's just split it evenly, make the math nice and easy. What would each of those paths get? 2, right. Oh, hello, another junction. Split it evenly again. Yeah, 1 and 1. You could, but we don't need to because that just wraps around. So how much current is it round here, around the bend? Still 1 amp. Oh, another junction. How much in this little short spot? 1 plus 1 makes 2 amps. Come back together. 2 plus 2. You get the idea, right? And then at the end, 8 amps. So that's how the current behaves in a parallel circuit. It splits up. It comes back together. Very similar to the homework that you had, right? So, okay, what's the advantage here? The voltage behaves very differently. So I want you to imagine like a car battery, okay? There's terminals, got it? And I'm going to extend the terminals with like 2 big copper rods. And if this is a 12-volt battery, then when I hang like a light bulb between these, okay, right here, light bulb, what would the voltage be? I'm just going to extend the terminal. So what would the voltage drop be here? Starts with a T, ends with a weld. Yeah. Do you get that? If I just extend the terminal, it's just like attaching it to the battery, right? Directly. What if I then hang another light bulb right here? Now remember, I'm just extending the terminals. I can go this way, right, without even going through this path if I want to. So, and that's what the current does. It goes through whichever path is the least resistance. But the truth is that I still get 12 volts of pressure, of electrical pressure.
Pressure or actually?
That's what's put the power. That is what's pushing the current, is the voltage. That's what's supplying the current.
But there's more.
Yep.
So it doesn't.
No, what it does is it leaves consistent voltage. So the voltage in your outlets at home is 120 volts, and every single appliance that you plug in a parallel circuit ends up pulling 120 volts. So it's a nice consistent voltage. It allows us to rate our appliances based on that, okay? The drawback is that it actually will pull more and more current every pathway. Think about like a river. and the river like opens up and splits off into a bunch of parallel pathways, what's going to happen to like the speed of the water and the amount of water that gets dumped? Better? More? Faster? Yes. So the same thing happens here if we keep hanging light bulbs. Anybody in their house have like an octopus spot? You know what I mean? Like, oh, it's that one spot where I've got like a circuit like with extra plugs. If you keep adding more and more pathways, you're opening up the river and you get lots of current. And if you get too much current, you can get a fire, correct, because it's too hot. Too much current pushing through those wires. And that's what circuit breakers are for. They're a protection. Unless you're my grandmother and you're too cheap, because you grew up during the Depression, see how it's all coming home, to buy a fuse, and so you stick a penny in your old fuse, because pennies are copper and they conduct electricity, and then you burn your house down. But you save the 40 cents for that new fuse. So, let's do the math for parallel circuits now.
Did you really burn her house?
No, we smelled the insulation burning before it actually happened.
That's so sad.
I know. It actually was my first lesson. I was about 8 years old. My first lesson in electricity. It's kind of cool. It's probably one of the reasons I'm a physics teacher, because my grandpa taught me. So these are resistors instead of light bulbs. You get the analogy here? Very similar. And let's say this is a 6-volt battery, okay? And I'm going to make this a 2-ohm resistor and this a 2-ohm resistor. Got it? So if I have 6 volts, 6 volts, 6 volts, 6 volts on these parallel pathways, 6 volts is dropped here, so I'm going to drop my voltage. I'll do my little spider thingy. 6 volts here, 6 volts here, right? How much current, using Ohm's law, V equals IR, solve for the current, how much current gets through if I have 6 volts pushing through a 2-ohm resistor? No, you're solving for I. 3. 6 equals 3 times 2. So 3 amps gets through here, 3 amps gets through here, right? Does that make sense?
Is the A?
3 amps is the current, that's I. That's I. R is the little squiggly thing, the ohms, horseshoes, and V is voltage. So now let's go back to our junction. So I have 3 amps, 3 amps, 3 amps, coming here, 3 amps here. Oh, how much came out of the battery then? This is the current. So I have 3 amps right here, 3 amps over here. How much out of the battery? 6. And then 3 amps coming back together here and here. How much going back into the battery? 6. Correct. So if I didn't look at any of this and I just looked at the voltage and the current, what would the overall resistance equal? V equals I times R. What's R? 1. Guess what happens when you put parallel resistors together? 1 over R total equals 1 over R1 plus 1 over R2, dot, 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 as many as you want. So 1/2 plus 1/2 equals 1 over what? What's 1/2 plus 1/2? 1. So the denominator is 1. That's the total resistance. This is the equation that we use for parallel resistors. But you figured it out without even knowing the equation, right? So I want you to do this for homework.
The back side of that sheet?
No. The back side of that sheet is completely optional, or the front side, or whatever you want. That's just more of those circuit, like pathway examples, because you'll have one of those on the test. Parallel circuits is right here. So on your way out, you can come grab it. On the back, it says compound circuits. That will scare you anyway, so don't do the back. Okay?
And if we figure out the extra credit, we can turn that into.
Yeah, you can turn your extra credits.
And I need blood yesterday also.
Okay.
I have a.
How do we,
All right, good.
how do we do, this here, okay.
That one, you have 18 and, like the 5 is internal, so 18 plus 5 is 23, right? You have 23 coming in, 13 going out, what would that leave here?
Wait, no, wait.
23 coming in, 13 going out, right.
Okay. So then is the final 18 or is the final 23?
Tell me.
23.
No? Yep, because you got 5 going out here. So you have 13 coming in, 10 coming in, that's 23. Yep, that's 13 minus 10.
All right.
Mhm.
Alright.
Yep. And AJ and Spence, you got to the finish line very beautifully today, but you're on my, I don't think this is gonna work list. No, I'm serious. End of class was, I could tell you were totally with me, but not so much at the beginning, right?
Yeah.
Yeah. What were you doing to your phone?
Well, it's already broken. So I thought I might as well just have a little fun.
Really? I would have never found her.
Somebody, we all could see it though, so somebody would have.
Somebody would have told me.
I didn't even realize that. You should just leave it up there and see what you want.